Section 8.3 talks about polar form of a complex number and DeMoiver's theorem. Now, DeMoiver's theorem is really not going to exist because we're going to use the Euler formula, and that's going to pretty much replace DeMoiver's theorem. I'll tell you what it is when we get there. So, the cosine of theta plus I sine of theta is equal to e to the I theta. E is the same exponential constant, 2.712 ... It's the irrational number. E named after Euler. I is the square root of -1. And I squared equal -1 from algebra. That's the same I. So e raised to the imaginary number I times x is cosine of x plus I the sine of x. Now, a complex number has this form. Some books write it this form. Some books call it rectangular form because it has an x and a y. A and B the same deal. There's A, there's B. Oh, there's x, there's y. The I is nothing more than the complex axis. And this is nothing more than the real axis. And that's what this says. This says x is the real axis, y is the imaginary axis. So we're going to start off by plotting, and that turns out to be the key. 8,1, 8,3, and 9,1. Vectors, complex numbers, and polar coordinates are identical. They just use different notation, but it's the same idea, but each has its own application. So when I say z equal 1 plus I, we're really talking about 1 for x and 1 for y. 1, 1, there it is. That's A. Nothing more than our rectangular. That's why some books call this rectangular form, and they call this polar form. How about this right here? Well, this is really the point -3, 2. -1, -3, -1, -2, -3, 1, 2. This is point B is right there. C is at -3i, no x, 3y. -2, and this is really -3, -3. The key in all of these three sections is to plot the point. And now we're talking about if you have x plus iy, well, think of it this way. There is x, there is y, or a and b. You could find r and you could find theta, except they call r the absolute value of z. Absolute value of z is the square root of a squared plus b squared. Hey, that's R, that's the hypotenuse. And tan of theta equals the opposite over the adjacent. Rings a bell? Their catch, theta has to be in positive rotation all the time, and it has to be between 0 and 2 pi. It can't exceed 2 pi, not in complex land. So, we're gonna pretty much repeat what we did with polar in section 8.1. Pretty much, I'm giving you r, x and y, give me r and theta, I give you r and theta, give me x and y. And the same formulas hold. So, write each complex number, this is a complex number, in polar form. Some books say write each rectangular form in polar form. No biggie. Key is a rough sketch. It's not asking for a graph, and that's not part of the problem. But using the formulas alone is never sufficient. Move 1 to the right, 1 up. 1, 1. So, write it in complex form. We know how to find r. Keep in mind, in complex numbers, they call r the modulus of z. Since it's an absolute value, it's always positive. Could equal, I suppose. And theta is always, they call it the argument. So modulus argument. We called it r, we called it theta. Here they call it modulus argument. In vectors they call it magnitude and direction. Same exact thing. So what's r? Well, we know that r squared is 1 squared plus 1. So keep in mind, I never comes into play. R is only there for reference. And can you guess if the opposite and the adjacent are the same? Doesn't that mean that theta equal pi over 4? Write each complex number in polar form. So we know that x is going to equal r the cosine of theta, y is going to equal r the sine of theta. So we're going to write this is z equal r, which is radical 2 times the cosine of theta, cosine of pi over 4, plus I the sine of pi over 4. And let me show you something that I think you're going to find very useful. That's going to save you memorizing 7 different formulas. By Euler's formula, cosine of an angle plus I times the sine of an angle is e to the I times that angle. This is e to the pi over 4i. When they say write it in polar form, the back of the book, you look at it, this is what they have. We're going to write it this way. Even though this book doesn't talk about Euler formula, we're going to use it anyways. Why? Because that's going to save us 7 formulas. It's going to save us on the addition, subtraction, multiplication, division, raising to a power, 6 formulas, and finding the roots of unity. Alright, how about this problem? Well, again, a rough sketch will do the graph. You really should get into the habit of plotting points and drawing the rectangle. I've been trying to enforce that forever. Hopefully I made a dent and you're really taking that seriously. That plotting, even though it's not required, I know it's not required, but it's going to save you a lot of pain on the long run. It's going to combine the 3 sections and make them repetition, meaning review one from another. So 1, this is nothing more than 1 to the right and 1 down. Very good, I got it. I know r equal 2. So I'm going to think this is r e to the I theta. R is radical 2, I know that, so it's radical 2 e. I know the reference angle is pi over 4. What's pi over 4? Again, remember, you want in positive rotation. Isn't that 7 pi over 4i? And that would be my answer, and I'm done. So we did that already in section 8.1. The back of the book will have radical 2 into cosine of 7 pi over 4 plus I the sine of 7 pi over 4. And no big deal. This is 1 over radical 2. This is 1 over radical 2. This is positive. This is negative. If you distribute that in, you'll get a 1 minus I at any given time. So those are the same thing, but there is a use of polar form that reals don't have and complexes don't have. Numbers, that is. How about this problem? I'm going to move radical 3 to the right, 3 to the right, and negative radical 3 down. This r is slightly different. R squared equals 9 plus 3, which is 12. R equal 2 radical 3. So this is 2 radical 3e. I need the angle. Well, think about it. Whatever this is, whatever this is double it, and this is radical 3 times, radical 3 times that. So that makes it, or you could draw the triangle if you really wish. You could say 30, 1, 2, radical 3. Tan of theta is negative radical 3 over 3, which is 1 over radical 3. Tan of 30 is 1 over radical 3. So it's a reference angle of 30 degrees. If you want to use degrees, I don't mind, it's fine, but they use radians on the most of the part. I'm flexible either way. What is pi over 6 in the 4th quadrant? 11 pi over 6i. I'm not going to keep on writing this. This is the last time I'm going to write this. In the back of the book, they're going to say this is 2 radical 3 into the cosine of 11 pi over 6 plus I the sine of 11 pi over 6. That's the same thing as what we have. This is how we're going to write our answer. How about the next set of problems? I brought you the special cases. They turn out to be the messiest if you just use formulas, which I'm trying to persuade you not to do that. 3i, that is going 1, 2, 3 up. That's simple. R equal 3. And what's the angle? 90 degrees? Or pi over 2? E to the pi over 2i. Done. How about if I had negative 2? Doesn't that mean you move 2 left? You're right there. Isn't the radius 2? And what's the angle? Pi I. And how about this problem? Well, not many of those, but every now and then you come across those. You distribute that in, that's 3i minus 3i squared. That's 3i minus 3, but I squared is negative 1. That would be a 3 plus 3i. So it's a habit to write the real first and the complex after. So this is move 1, 2, 3, and 1, 2, 3. I'm right there. Can you tell what R is? Three radical 2. Yep. And theta, if the opposite and the adjacent are equal, I have a reference angle of pi over 4. What does that mean? I could write this as 3 radical 2 e, and since I'm in quadrant 1, pi over 4i. And that's pretty much it. So this is going from x and y to r and theta. We did that back in the days, if you recall. Now, let's play with this a bit. Go the other way around. Some books say write z in rectangular form. Well, we had, remember, this is the way they write this. So we had it in rectangular, we wrote it in polar. Now we're going from polar to rectangular. This problem could have been written like this. And you're going to get used to knowing that e to the pi over 4i is cosine of the angle, the number in front of I, plus I times the sine of that. Well, here, this is 2. Cosine of pi over 4 is radical 2 over 2. Radical 2 over 2. And if you distribute that in, isn't that radical 2 plus I radical 2? Again, some books call this the rectangular form. No biggie, we're not going to argue back and forth over that. That's really simple. And how about here? Well, we know how to do this. This is really 8 times. And this has a reference angle of pi over 6. There's pi over 6. 1, 2, radical 3. So cosine is the adjacent over the hypotenuse. Sine is the opposite over the adjacent. 11 pi over 6. So this is going to be 4 radical 3 minus 4i. And I'm going to use the triangle for number part. Oh, I didn't change them. That's a D. For C, again, that's really simple. That is 15. Pi over 3 is a 60 degrees right there. Cosine is 1/2. Sine is radical 3 over 2. Except 4 pi over 3 is in quadrant. They're both negative. So this is negative 15/2 minus 15/2 radical 3i. It's a good habit to write it in the form of a plus bi. Not that it matters, But it's mathematically more correct. And how about here? Well, z is going to equal 3 times cosine of 120. 120 has a reference angle of 60 degrees. There's 60 degrees. Cosine is the adjacent over the hypotenuse. Sine is radical 3 over 2. In the second quadrant, cosine is negative, sine is positive. So this is negative 3 halves plus 3 radical 3 over 2i. Alright, we're going to stop this video here.